So chapter 12 deals with rates. Now, what rates are is simply the speed of a chemical reaction. And that's something we have not talked about yet. So we've talked about how to balance chemical equations. We've talked about the energetics of chemical reactions. We've talked about a lot of different things, but we haven't talked about how fast chemical reactions actually occur. And that's a big deal. Some chemical reactions occur in a fraction of a second. Other chemical reactions can take up to millions of years and everywhere in between. So chemical reactions can have widely different speeds to them, widely different rates. And generally speaking, what determines the rate of a chemical reaction, how fast it goes, is something called the collision theory. So in the collision theory, let's say we have two reactants here, A and B, that are going to react together to form compound C. Well, the collision theory simply states this. So imagine this is compound A and this is compound B. The only way these two compounds can react is if they actually come into physical contact with each other. If one's over here and one's over here, they can't possibly react. They have to actually collide with each other for the reaction to take place. So, according to that collision theory, anything that would facilitate A and B crashing into each other is going to make our reaction go faster. It's going to increase the rate. And that's generally what we want to do here. There are some limited circumstances where you may want to slow down a chemical reaction, but most of the time we want to speed it up. So I'm going to open up to the floor here. What do you think we could do to facilitate a collision between these two chemicals, between A and B? And I'll give you a hint. One way of doing this would be to make sure they're moving around faster. So who can tell me what we could do to make these molecules move around faster and make it more likely they're going to crash into each other?
Is it heat them up?
Heating them up, exactly. That's the big one here, heat. So as we know, the hotter a chemical is, the faster its molecules are going to be moving around. So if we heat up A and B here, they're going to be moving around a lot faster. And if they move around a lot faster, that's going to make it a lot more likely they're going to crash into each other. And when they crash into each other, they can react. And there's a rule of thumb when it comes to temperature here. So every 10 degrees C increase in temperature is going to double the rate. So in other words, every 10 degrees C, you increase the temperature, the reaction will occur twice as fast. Now we're going to see this a lot as you continue in chemistry, especially when you get to organic chemistry. Almost every reaction we do in organic chemistry, we heat the stuff up. And that'll make the reaction go faster. And as an example here, let's say you're doing a reaction initially at room temperature at 20 degrees C. If you just raise that to 30 degrees C, the reaction's going to go twice as fast. Well, compared to 20 degrees C, let's say you raised it up to 40 degrees C. How much faster would the reaction go then? Well, in that case, you have two doublings. So a reaction will go 4 times as fast at 40 degrees C as it did at 20 degrees C. So heating up is big. Heating up reactions will speed them up very, very well. And this is just a general rule of thumb, so don't absolutely quote me on this, but generally speaking, every 10 degrees C increase is going to double that reaction rate. All right, let's think of something else we could do to speed up a reaction. So one way is to get the molecules to move around faster. That's heat. Another way to increase collisions would be to cause more crowding, to just have more A and B present. So how could we make sure there's more A and B present here? Any ideas?
Increase the, oh crap, I forgot what the word is. Basically, the pressure?
The pressure is one way, but that's only going to work with gases. So that will absolutely work if you have at least one gas as a reactant. Increasing the pressure will cause more crowding. Absolutely. But there is a more general way we could increase collisions. And think about what we were talking about prior to break here. All those different units of molarity, concentration. So that's going to be our next big one, concentration. So the more concentrated our reactants are, the more crowding there is in solution, and the more likely things are to crash into each other. And mathematically, that's what we're going to be focusing in on in chapter 12, the effects of concentration. So let me give you a specific chemical reaction here. So here's a specific chemical reaction we can talk about here. And of course, before we do anything else, always make sure your chemical reaction is balanced. Is this guy balanced? Yeah, pretty easy one this time. So what we're going to do here is we're going to figure out what effects changing concentration will have on this particular reaction. And to do that, we can look at our reactants individually and classify them into one of three categories. Those would be 0th order, 1st order, and 2nd order. So every reactant we see in chemical reactions can be classified as 0th order, 1st order, or 2nd order. And when you get into more advanced chemistry, like physical chemistry, for example, we'll see there's fractional orders we can get to as well, things like square root of 2 orders, stuff like that. We are not going to worry about that in Gen Chem 2. So remember this, in general chemistry 2, for our purposes, every reactant is going to be one of these three orders. The most straightforward one is 1st order. And what 1st order says is this: if the concentration is doubled, rate also doubles. And this is the most common order we'll see in reactants. So again, if you double the concentration, the rate or the speed of the reaction will also double. Now, this doesn't just occur for doubling. Let's say we tripled the concentration. Well, if you triple the concentration of a 1st order reactant, the rate will also triple. So in 1st order, whatever you do to the concentration is also going to be done to the rate. Well, generally speaking, increasing concentration increases collisions and increases rate. But as we've already learned in chemistry, there's always exceptions. So it is possible to have what is called a 0th order reactant. And in that case, if concentration is doubled, good thing this isn't a spelling class. So in a 0th order reactant, if the concentration is doubled, the rate is going to be unchanged. And it doesn't have to be doubled, so if you tripled the concentration, the rate would still be unchanged. So this seems to violate what I was talking about with the collision theory, but I'll talk a little bit later, actually in our next lecture, about exactly why this is possible. So generally speaking, if you double the concentration, rate will also double. But it is possible for rate to be unaffected by concentration in certain circumstances. Now that brings us to our 3rd possibility, 2nd order. That's a bit trickier. So let's say, again, we're going to double the concentration. Well, in this case, rate will increase by a factor of 4. So if we double the concentration, the rate will quadruple. What we're actually seeing is a squared here. So let's say instead of doubling the concentration, we tripled the concentration. What would be the factor that the rate would go up in that case? Any ideas?
Is it 9?
Exactly. So if the concentration is tripled, rate will increase by a factor of 9. So that's the nature of second order. So whatever you do to the concentration, the square will be done to the rate. So if you quadruple the concentration, the rate would go up by a factor of 16. So there it is. So as we look at these various effects of concentration on reaction rate, every single reactant we see will fall into one of these three categories. And you'll have to identify which one each reactant is. So given all this, let's look at a specific problem involving these concepts. So back to this chemical reaction here, we want to figure out what is the order of each of these two reactants. What's the order of nitrogen monoxide and what's the order of chlorine? In order to do that, in order to figure out what order each reactant is, we're going to have to go into lab and do some experiments. So what I'm going to do here is I'm going to alter the concentrations of NO and Cl2, and we're going to directly measure in lab what effect that has on the rate. And I'm going to do as a first experiment a baseline. So in my baseline here, I'm going to use the same concentration of both of my reactants and see what the effective rate is. Now, what about this here? This is 2.0. Don't we need units? Well, despite all the concentration units we talked about before break, as it turns out, most of the time in chemistry, we just use molarity. And we've got a quick, easy shorthand for that. Anytime you draw something in brackets, like I've done here, that means concentration in molarity. So the fact that I drew NO in brackets here means this 2.0 is molarity, moles per liter. So I'm going to start with the same concentration of our two reactants here, and I will experimentally measure the rate at which this product, NoCl2, is formed. And let's say in this case, this is our rate. Now, what does this mean here? Well, the rate is in molarity per second. That tells me that under these conditions, that NoCl2 product is going to form at a rate of 1.2 times 10 to the negative first molarity, moles per liter, every second. So every second, we get an additional 1.2 times 10 to the negative first moles for every liter of volume. So there we have our baseline for our experiment here. We have the same amount of each reactant, and we now have a baseline rate. Well, now what we want to do is go on to a second experiment. And again, we want to figure out what is the order of each of these reactants. So what I'm going to do here in my second experiment is double the concentration of nitrogen monoxide. It's going to go up to 4.0 molar now. But as we know in science, when we're investigating something, we can only change one variable at a time. So I'm going to leave my chlorine concentration at 2.0 molar still. So everything's the same as experiment 1, except I just doubled the NO. Now let's say this happens. So I doubled NO, something happened to the rate. Now is the NO here 0th order? Why or why not? Any ideas?
It's not, because you have a change in rate.
Exactly. So if I had a 0th order for NO, doubling the concentration there would have a negligible effect on the rate. So we know that since we did have a substantial effect on the rate, this can't be 0th order. NO must be 1st or 2nd order. Now looking at this, we went from essentially 1.2 to 2.5. That is effectively a doubling. So that tells us that when we doubled NO, we doubled the rate as well. We would then say NO is 1st order. So whatever we did to the concentration was also done to the rate. Now, what about second order? We can quickly rule that out because if we doubled our concentration of NO and that NO was second order, we would see a quadrupling of the rate. And we definitely don't see that here. Now, I deliberately didn't write 2.4 here because I want you guys to realize we are reflecting experimental data here. So don't expect these numbers to be exactly what you would expect. Allow for a little bit of experimental error. So although 2.5 is not the 2.4 we would have expected here, it is approximately 2.4. So we definitely saw a doubling there when we doubled NO's concentration. All right, so NO then is a first order reactant. We're now going to go on to a third experiment, and referring to the original baseline, I'm now going to go back to that for NO. So NO is going to be 2.0 molar, just like it was in our baseline first experiment. This time, I'm going to double the Cl2. Now, what do you think is going to happen here? Well, let's say we get this. Now remember, we're comparing to the original baseline here. So avoid the temptation of comparing experiments 2 and 3. That's not going to be relevant here. We want to compare experiments 1 and 3. So when we held NO constant and we doubled Cl2, we definitely saw a change in rate. It effectively went from 1.2 to 5.0. So we can therefore rule out 0th order because definitely the rate significantly changed. And notice it's substantially more than doubling. And never lose sight of the fact that we can only have one of those 3 orders, 0th, 1st, or 2nd. So again, we ruled out 0th because the rate did significantly change. And just looking at that, obviously it's a bit more than doubling. So what is our last option?
Second order.
Yep, second order. So there we have it. So by doing a rate table like this, we can determine what the order is for each reactant. Obviously, we're not going to be doing experiments. This actually would have been one of our labs here. We're not going to be able to do this in class anymore. But on all future quiz, exam, and homework questions, what you will see is effectively the data that would have been collected experimentally. So get used to seeing this. This is what's called a rate table. So when you see a problem like this on your homework or on a quiz or exam, this will be the data you're given, the actual chemical equation and the experimental data that was collected by somebody else. And in this case here, we did have 2 reactants, and including that baseline, to figure out the order of those 2 reactants, we needed 3 experiments. As a rule of thumb, you'll always need a number of experiments, 1 more than the number of reactants. So if we have a more complicated reaction later that uses 3 reactants, we'd have to do a total of 4 experiments to work out the order of each of those 3 reactants. So there we have it. Now, ultimately, what we're trying to do here is construct what is called a rate expression. And here is our rate expression. The rate of this chemical reaction is going to equal some constant K times the concentration of our 2 reactants. But we can flesh out this rate equation a bit more because each of these concentrations of our reactants is going to be raised to the power of whichever order this reactant is. So as we just worked out, nitrogen monoxide is first order. So in our rate equation, we're going to raise the concentration of NO to the 1st power, which of course has no effect on it. It's just going to be whatever that concentration was. Chlorine, however, is second order, which means its concentration will have to be squared. Now, if we had a 0th order reactant, what is the value of any number raised to the 0th power? See if anyone falls for the trickiness there. So what do you get when you raise a number to the 0th power? You get?
Isn't it 1?
It is 1.
Oh,
Yep. Not 0.
It's 1, right? Yeah.
It is 1. Yep. So if we had a 0th order reactant in here, the concentration raised to the 0th power would just be 1, which means it would have no effect on our rate. That's exactly what 0th order says. But be careful, raising something to the 0th power is not 0. That would mean our rate was 0 as well, and that would not be correct. So in this case here, our rate is going to be equal to this constant K times the concentration of NO raised to the 1st power and Cl2 raised to the 2nd power. Well, our next step here, now that we've worked out the orders of both of our reactants, we now have to figure out what a numerical value for this constant K will be. And what we'll need to do is simply pick one of the experiments on your problem here. I like to do the first one, that baseline, just to be consistent. And what we'll need to do is plug in all of those values and simply solve algebraically for K. So there's the rate for experiment 1. And we're going to be solving for K. And in experiment 1, our NO concentration was 2.0 molar. And our Cl2 concentration was also 2.0 molar, but it was squared. So algebraically, solve for K. I'll give you a minute to do that. Okay, and so the calculator answer I get is going to be 0.015. So of course, 2 squared was 4, and 4 times 2 was 8, and I just did 1.2 times 10 to the negative first divided by 8. Make sure when you're working with scientific notation, you do put the scientific notation term in parentheses like I showed here. That avoids some nasty calculator errors. And how many sig figs should we have here? Well, obviously 2. But when you're solving for K, as it turns out, this is just a constant we're going to use to get other answers. So don't unnecessarily round K. If our K here had come out to say 3 or 4 sig figs, I would leave it at 3 or 4 sig figs to reduce rounding error later. Don't worry about sig figs with K too much. So this numerical value for K was pretty easy to get. Here's the really tricky part. What is the units for K going to be? Well, looking at our equation, so rate here, remember, was in molarity per second. And by the rules of algebra, our units to the right-hand side here have to also be molarity per second. So we've got mystery units for K here, which we're trying to figure out. Our NO concentration was molarity to the first. And our Cl2 concentration was molarity to the second. So what would have to be the units for K to make sure our units on the right-hand side total up to be just molarity per second? Well, we'll have to put a seconds down in the denominator. That's definitely going to be true. And we only want a 1 up in the numerator. So for all these times where you need to calculate the value for K, it's always going to have the same general form, a 1 in the numerator and a seconds in the denominator. The difference here is going to be how many molarities do we need to cancel out. So how many molarities do we need in the denominator here to finish out this equation? Who can tell me? Well, notice we ultimately need just 1 molarity up in the numerator, but we have currently molarity cubed. So that means down in the denominator here, we're going to have molarity squared. That will cancel out this molarity, and ultimately we'll just have molarity per second on each side of the chemical equation. So in this particular instance, our units for K is going to be 1 over molarity squared seconds. And K is a constant here, and constants always have goofy, weird units like this, and they're there purely for dimensional analysis purposes. It's just to make sure that when you plug K into your equation, your answer will have the correct units. So putting this all together, I now have a completed rate equation for this problem. So our rate is going to be equal to constant K, which we've just worked out, with its units. And there it is. Now, why did we do all this? Well, believe it or not, the main goal in chemistry is to avoid going into lab. So we initially had to do these 3 experiments in lab to collect this data. But now that we've done that and constructed a rate equation, we can now solve for the hypothetical rate for any given concentrations. So let's say I want to do an experiment 4 here. And let's say I want to have a concentration of 3.0 molar in NO and 2.5 molar in Cl2. I'll give you a second here. See if you can calculate what this rate should be, given our rate equation. Okay, so it's just a matter of plugging those new concentrations into our rate equation, and there's my calculator answer. Now remember, we didn't really worry so much about sig figs for K because that's just an intermediate in the calculation, but once we get to our final answer, we should definitely make sure we have the correct sig figs. And clearly in this problem, we should have 2 sig figs. All right. Now, what about our units? Well, remember, that's why we had the units for K that we did. Doing all these together, we see the units left over after canceling are molarity per second, exactly what we'd expect for a rate. And to make it consistent with the other rates we see in our rate table, I can put this into scientific notation. And there we go. So that is why we do these rate calculations. So we do a couple of experiments in lab, and then after we do those experiments and construct this rate equation, we now can leave lab and we can theorize what the rate would be with any given concentration of our reactants. But there are some definite limitations here. What I've done here is what is called interpolation. Notice that I was exploring in my experiments concentrations between 2.0 and 4.0, and that means for any hypothetical reaction I calculate here, the concentrations should be between those, should be in that range, between those values. So for maximum accuracy, our concentration should be between those established values of 2.0 and 4.0. That is called interpolation. If I try to do concentrations outside that range, like maybe a concentration of NO that was 6.0 and Cl2 that was 7.0, that would be extrapolation. That would be a lot less accurate. So generally speaking, we want to stick within the concentrations specified. Now there's another big limitation here, and that is, what was the other big thing that affects rate? Not just concentration, but
Temperature.
Temperature. So I'm assuming that everything we're seeing here, all 4 now experiments, were done at the same temperature. So any good rate table should specify that. So I'm going to say that all these experiments were done at 22 degrees C, and that means all of our data, including this rate equation, is only accurate at that one temperature. If we came back to lab the next day and it's now 26 degrees C, we would have to do our rate table over again because K will actually have a different value in that case. So whenever you see a rate table like this, it's always at one specific temperature. All right. Now let's talk a little bit more about rate here. So when I say rate here, what I mean is rate of formation of this NoCl2 product. That's what I'm talking about. So how many moles per liter per second are we forming of that product? Now, let's see what I was going to say about that. Oh, now here's the problem with this. So let's say our NO and Cl2 are coming together and they're forming NoCl2. Well, as that reaction occurs, what's going to happen to our concentrations of NO and Cl2? Who can tell me? Wake up, everybody. Well, as we're making NoCl2, aren't the concentrations of NO and Cl2 going to decrease as they get used up? So really, when we talk about rates here, it may not be explicitly stated, but what we're always saying here is initial rate. This is something we say this is the rate at time 0, the rate that occurs when the reaction is just beginning. So actually, as this reaction proceeds, this rate is going to decrease because the concentrations of NO and Cl2 are going to go down as they're used up, and so the rate will steadily decrease. And eventually, we're going to run out of NO or Cl2, and once we run out of one of those 2 reactants, the rate is going to go down to 0. So when we calculate rate here, this is the initial rate. The rate the reaction starts at, the rate will slow down with time. Now, let's say we wanted to mathematically model this. How could we mathematically depict the rate changing as a function of time? Give you a hint, it's an obscene word that begins with the letter C. It's your most favorite math class.
Calculus?
Calculus, yes. So this is specifically a calculus-free course. We're only doing algebra here, and that's why we're only going to deal with this initial rate. Any of you guys who are lucky enough to take physical chemistry later on in your academic career, in physical chemistry, we'll actually use calculus to see how the rate changes as a function of time. But for now, we're just going to keep things simple, and we're just going to talk about this initial rate. Thus, we can factor out calculus and just stick with algebra. Makes things a lot easier. Okay, so let's trial this with a new problem. Okay, so we've got a new reaction here. Anything we should do before we move on?
Balance.
Of course. So I would just say the least common multiple here being 6. If we have 3 Cl2s and 2 PCl3s, we got 6 chlorines on each side, and we'll also need 2 phosphoruses on each side. So as always make sure your chemical equation is balanced before you do anything else. Sadly, all the homework problems in your book will be pre-balanced, so I apologize for that.
For the chemical equations, do they always have to be gases, or can they be other? Can they be like solid or anything else?
Well, as it turns out, they can be, but we'll talk about that on Thursday. That's the next level of complexity. Yeah, we'll get there. I'm leaving things simple for now because they're all gases, so we can speak in terms of molarity for each. But yes, that will change in the future. All righty, so let's do up a rate table again. And you could be doing this experimentally if we were actually in lab, but again, for our purposes, someone else is going to do these experiments for you. So in order to work out the order of our two reactants here, how many experiments will we need to do?
3.
3, yep. It's always one more than the number of reactants. And of course, most chemical reactions have 2 reactants, but if you encounter one that has 3 or even 4, just make sure you do one more experiment than the number of reactants. You have to account for that baseline you have to do first. Now, before we move on to the actual rate table, I want to point something out here. Now that we have a more complicated chemical equation up here, we can think in terms of the coefficients in the equation. Let's say, for example, that our PCl3 here is forming at a rate of 6.6 times 10 to the negative 3 molarity per second. Let's just pretend that's our answer. What is the rate of disappearance of Cl2? Who can tell me that? So the 6.6 times 10 to the negative 3 molarity per second is the rate of appearance of PCl3. What is the rate of disappearance of Cl2? Who can tell me? All right, give up. So if our PCl3 is forming at this rate, we see there is a 2 to 3 relationship stoichiometry-wise between the coefficients of these two materials. So if we've got a 2 to 3 ratio, that means the rate of disappearance of Cl2 is going to be this. You can even put a negative sign in the front if you'd like. So as we make 6.6 times 10 to the negative 3rd molarity per second of PCl3, we will lose 9.9 times 10 to the negative 3 molarity per second of chlorine. What would be the rate of disappearance of phosphorus? Who can tell me that?
It's the same, right? It's a 1-to-1.
So it's the same as what?
You have a, maybe I'm getting this wrong, but you have a 2 on one side and the 2 on the other, so it's 1-to-1, right?
Exactly. Yep. There. So since we have a coefficient of a 2 in front of the phosphorus and a 2 in front of the PCl3 product, we would say the rate of appearance of PCl3 is going to be exactly equal to the rate of disappearance of phosphorus. So just bear that in mind as you look at these rate tables. Generally, the stated rate is the rate of appearance of product, but using your balanced chemical equation, you can also figure out the rate of disappearance of your reactants. It's all down to the coefficients in that balanced chemical equation. All right, let's get back to the actual rate table here. So we're going to start out with a baseline, and this time I'm going to do my baseline at 4.0 molar for our two reactants. Generally speaking, your baseline should have the same concentration of each reactant. It makes your math a lot easier. And let's say here is our rate of appearance of PCl3. So there's our baseline. That should be a 9, by the way. So now in reference to that baseline, I now want to alter my phosphorus. Let's say I'm going to do this. I'm going to move the phosphorus concentration up to 12.0 molar, but I only want to change one variable at a time, so I'm going to leave the chlorine exactly the same. So what effect is this going to have on our concentration? Well, let's see. Or rate, I should say. Well, it turns out experimentally, we got this. Now for our third experiment, we're going to want to hold our phosphorus concentration the same as it was in the baseline. And just to be a little obnoxious, I'm going to double the chlorine this time. And let's say when I double the chlorine, this happens. There. So on a homework problem, for example, or something you might see on next week's quiz, this is what you'll be given, this data right here. We can't collect it experimentally, so we have to rely on someone else to have done it for us. What I want you guys to do in the next 5 minutes is I want you guys to figure out what the order is of each of our two reactants, the phosphorus and the Cl2. So is each reactant 0th, 1st, or 2nd order? I'll give you guys 3 minutes to work that out, and I'll come back at 12:22.
I got second for phosphorus and, or no, first for phosphorus and second for Cl. Anybody else?
That's what I was thinking as well.
All right. Let's take a look. I deliberately made the math a little bit harder than it was in the previous problem to kind of mess with your brains a little bit. Here's a good, easy way of figuring these out. So looking at experiments 1 and 2 here, and that's what we're going to be looking at to work out the reactant order for phosphorus, because we're leaving Cl2 constant. And remember, we're tripling the phosphorus concentration. So a good, easy way of figuring this out, rather than eyeballing it, is simply do the math. So when we tripled our concentration of phosphorus, what happened to our rate? Well, simply do 2.9 times 10 to the negative 2 divided by 9.7 times 10 to the negative 3. And when you do this in your calculator, of course, you're not going to include the units in your calculator, but make sure you do include parentheses to avoid weird little math errors. So if you type just what I have there into your calculator, what do we get as an answer? Well, my calculator answer is about 2.98969, which is approximately 3. Ooh, that's a nasty 3. So what is the order of our phosphorus reactant then? It must be first order, because notice I tripled that phosphorus concentration and the rate was also tripled. So if whatever you do to the concentration is also done to the rate, that is going to be first order. You guys said that, right? So you're right on phosphorus. Now let's take a look at the chlorine. For chlorine, we're going to have to compare experiments 1 and 3 this time. And again, if you can't eyeball this, try doing it mathematically. So going from experiment 1 to experiment 3, we doubled our Cl2 concentration from 4.0 to 8.0. In that same interval, what happened to the rate? Just do 1.9 times 10 to the negative 2 divided by 9.7 times 10 to the negative 3, making sure to include those parentheses. What do we get? And my answer here is approximately 2. It's about 1.958, but it's approximately 2. So then, what can we say about the order of Cl2?
Is it also first order?
It is also first order. Yep. So be careful. A lot of these times you can eyeball these things if the numbers are reasonable, but if the numbers are kind of screwy the way they are here, try the mathematical method instead to really see what this ratio is. And remember, your answer has to be 0th, 1st, or 2nd. That's about all we can have here. So simply see what effect changing your concentration had on that rate. So in this case, going between experiment 1 and experiment 3, we doubled the concentration of chlorine, and that also doubled the rate. So we would therefore say Cl2 is first order. So we can put all this data together now and come up with a rate expression. So rate is going to equal a constant K times the concentration of each of our reactants. And now we can flesh this out a little bit more. Since we know that the P and the Cl2 are both first order reactants, we're going to raise each of those to the first power. Next thing we want to do here is figure out what the value for K is going to be. So what I want you to do is take a couple more minutes here, figure out what the mathematical value for K is, and very important, make sure it has the right units as well. Technically speaking, you can use the data from any of these 3 experiments to do this, and your K will be approximately the same in each case. I'd recommend for consistency, just always use that baseline first experiment. So plug that data in, see what your numerical answer is, and do a little dimensional analysis to make sure K has the right units. I'll give you another 3 minutes to do that. Go ahead and try it. All right, let's take a look here. So again, I'm just going to plug in our data from the baseline, experiment 1. So there's our rate. We're going to be solving for K. And our P concentration was 4.0 raised to the first. And, oh, we ran out of room for the chlorine. And chlorine's also going to be 4.0 raised to the first. So solving algebraically here for K, we're going to get this. There we go. So that's what the calculator tells me. And notice I went out to an extra sig fig here, and that's fine because K is in the middle of our calculation here. We don't want to add too much rounding error. So going to an extra sig fig is good here. So that's what my calculator said. What about units? Well, breaking this down again, we know our rate on the left has to be molarity per second. And there's our mystery units for K. And we have molarity to the first and molarity to the first out to the right. So K has to be a 1 in the numerator, an S in the denominator. In this case, how many molarities do we need in the denominator of K to make sure the equation is equal on both sides?
Just one?
Yep, just 1 molarity this time. There it is. And that way on both sides of this equation, we have molarity per second. So that tells us our units for K here are going to be 1 over molarity seconds. At this point, we now have a completed rate expression. So rate equals that constant K times the concentration of phosphorus raised to the first power and chlorine raised to the first power. So as long as we keep to the same temperature we use in this experiment, and let's say in this case our temperature was 18 degrees C, for example, as long as we do our experiments at this temperature, we can expect this rate equation to give us reasonable approximations of what the rate would be. Again, with a limitation that we want to interpolate data here. So our concentration should be between about 4.0 and 12.0 for best accuracy. If we go outside that concentration range, we'll be extrapolating, and that will have more error. So given this, let's try a fourth experiment where we have a concentration of phosphorus that's 5.0 and a concentration of chlorine that's 6.0. Go ahead and plug that in there and see what the rate should be theoretically. Try that for a couple minutes. Maybe a couple of minutes was kind of excessive because this is a pretty simple one. There. And since we're coming to the end of our calculation here, we would now round to the correct sig figs, which would be 2. So our predicted rate for those two concentrations is right there. And a good way to check for math errors here is make sure your answer seems consistent with the rest of that rate table, and it certainly does seem to be consistent there. So it seems likely that is the correct answer. All right, guys, any questions on this so far?
On a quiz or exam, we would be expected to figure out the rate of the fourth. Is that what we would be figuring out on a quiz or exam, the fourth rate?
Yep, exactly. So I would give you this information right here that I circled in purple. That's what you would get on the homework problem or an exam or quiz problem. and everything else you would have to figure out. So this would be a multi-step problem. You'd have to figure out the order of each reactant, then solve for a value of K with the correct units, and then, yes, do a fourth experiment where you plug in new concentrations and predict what the rate would be.
The new concentrations would be given to us, or do we just plug in?
It would be given to you, yes. So
Okay.
what's circled in purple would be what I gave you in the problem. And so in this case, part A of the problem would be figure out the order of each reactant. Part B would be to solve K with the correct units. And part C would be, assuming these new concentrations, what would be your theoretical initial rate?